Hello everybody, welcome back to the Professors DuBois channel. I'm Professor Victoria and this is Professor Corey, and today we're going to be talking about orbitals and in particular the nodes of orbitals.
Alright, so prior to this video lecture we were talking about places where we would find an electron. So we were using quantum numbers to designate regions of high probability of finding an electron. Well, there are also regions where there is no probability of finding an electron. What we could say the electron density is 0. So this is really based on quantum mechanical wave functions, and that's really hard to understand, and I'd really like to just make this easy. So let's think of these nodes as either being a radial type, and you can think of like a soap bubble. It's like a circular type of area or region.
Spherical.
Or planar, and we're thinking about like sheets of paper, like in a plane. So we're going to look at nodes from this perspective, but realize this is based on quantum mechanical wave function.
We have to consider the electron as a wave. So we have wave-particle duality. So our waves, our electromagnetic radiation can be treated as a particle, right? A photon. Well, these moving matter can also be treated as a wave. And when matter has large mass, like a baseball, you throw a baseball, it has a wavelength, which is kind of strange, but its wavelength is somewhat meaningless because the mass is so high, but the electron's mass is so small that it ends up being that the wavelength is actually quite significant. So if you think of the electron as a wave, you can see where there's points that the amplitude is 0. So we don't have any amplitude at these points, and this is where we would have a node. So think about the electron as a wave in this orbital. And that's kind of a way to visualize what a node is.
So another way we can visualize it is just kind of by looking at these regions of high probability of finding an electron. And let's start with our p orbitals, or our dumbbell-shaped orbitals. And you can see here, if we took the 2p, there's actually a region through there where there's no electron density, and it's kind of hard to see in that image, but maybe if we drew it, yeah, there we go. So we've got a region there. Now look at those d orbitals, our clover leaf. If we could draw a clover leaf, you can see that there's actually 2 regions in there where there could be a planar node.
I wonder if I could just
change the color. Yeah, there you go. So there's a region there, and there's a region there. Now the spherical node is kind of hard to observe. You actually would have to like cut the sphere in half to take a look at the inside. And when you did that, you would see the nucleus, really tiny, and you'd see a region of high probability, the 1s, around it. Well, then there's a region where there is no electron density before the 2s orbital, the next, which is bigger and higher in energy. So a little hard to see the sphericals, but we have a few tricks to help you guys out.
Oftentimes you need to find the number of nodes. So how many spherical nodes are there in this orbital? How many planar nodes, or how many total nodes would there be in a certain type of orbital? And planar nodes are the number of planar nodes in any given orbital is equal to the number of L. So L is 0. Any s orbitals, there's no planar nodes, which really makes sense. If you think of a sphere, you're not going to be able to cut it in half with a piece of paper. So that kind of makes sense. So the planar nodes is equal to the number of L, and the radial or spherical nodes is n minus L minus 1. So the total nodes, if you added these together, the L and the minus L cancel, and your total nodes is n minus 1.
And just for clarification, this is the same L, the quantum number L that we were doing. Is that the angular momentum?
It is.
Yeah, so L, we can get this from n. So L can be anywhere from 0 to n minus 1. So recall that if L is 0, we call that an s orbital. And if L equals 1, it's a p. If L equals 2, it's a d. And if L equals 3, it's an f. And each of these has a shape. We have the spherical shape, the dumbbell shape, the clover leaf, and many shapes.
And lots of crazy shapes. Okay, so what type of orbital has two nodal planes, same as planar nodes?
Just to
S,
confuse
P, D,
you.
or F, right. So remember our planar nodes is equal to L. So we were talking about how when L is 0, it's an S, 1 is a P, 2 is a D, and 3 is an F. So if we were looking for 2, then that means it must be a D orbital.
A D orbital, cloverleaf. And we saw that it's pretty easy to visualize those two planar nodes in that cloverleaf shape.
And this would be any D orbital, so any of these. All right.
Okay, so this one has two spherical nodes. So the trick, the cheat here is the spherical nodes are equal to n minus L minus 1. So if we just go through each of these, and we know that, for the 1s, n equals 1, the L equals 0, that's the s, spherical, minus 1 equals 0. So this one doesn't have 2. Let's look at the 3s. We've got 3 minus 0 minus 1 equals 2. Looks like we found our answer, but let's check the rest. Because this gets kind of interesting, really. When we look at the 3p, we've got 3 minus 1, L equals 1 for the p orbital, minus 1, and we have 1. We actually have a spherical node in the 3p, and it's kind of hard to visualize. Let's look at the 5s. So we've got 5 minus L is 0 minus 1, so we have 4 spherical nodes in the 5s orbital. These are regions where electrons cannot exist.
Oh, no, you don't. All right, so here's the practice. Take some time, pause the video, and see if you can answer these questions. And here are your answers. Hopefully you understood nodes a little bit more than when you started. And check back anytime, and we'll have more chemistry coming your way with the Professors DuBois.
All right, thanks for watching.